Draw a circle on a piece of paper. It does not need to be a good circle. A rough, slightly wonky loop will do. Now, put a dot somewhere inside it. Somewhere near the middle, but not exactly at the center. That dot is you. That circle is everything you can see, everything observable, everything from which light has had 13.8 billion years to reach you. Now look at the circle's edge and ask yourself, what is on the other side? Your instinct, almost certainly, is to say, more paper, more of the same. The circle ends, but the paper continues, and the paper beyond the circle is presumably much like the paper inside it. Flat, uniform, extending in every direction. The edge of the circle is not the edge of anything real. It is just the limit of what the dot can currently perceive. This is, as it happens, the most likely answer to one of the deepest questions in cosmology. But it is not the only answer. And some of the other answers are so strange, so geometrically vertiginous, so philosophically unsettling that the more paper answer begins to seem, by comparison, like the least interesting thing the universe could possibly have chosen to do with itself. Because the universe did not have to be like paper at all. Space does not have to be flat or infinite or uniform or familiar. The universe might be curved in ways that bring distant regions back around to connect with nearby ones. It might be finite without having any edge or boundary. It might be one of infinitely many, separated from its neighbors by barriers that nothing can cross and from which no signal can ever arrive. It might be shaped in ways that mathematics can describe, but no human intuition can picture. And beyond all of that, beyond the geometry, beyond the topology, beyond the theoretical frameworks that physicists have spent decades developing, is the possibility that the question itself is harder than it first appears. That asking what lies beyond the edge of the universe requires, first, a very careful examination of what we even mean by edge, and universe, and beyond. This is the journey we are about to take. It will begin with what we can actually see. It will move through what we can reasonably infer. It will pass through the most ambitious and well-supported theories in modern cosmology, and it will end, as every honest account of a frontier science ends, at the boundary between what we know and what we can only wonder about. Somewhere beyond that boundary, perhaps, is the answer. The horizon. The universe has an edge, of a sort. It is called the cosmic horizon, or the particle horizon, and it is the boundary beyond which light has not had time to reach us in the age of the universe. The universe is approximately 13.8 billion years old. Light travels at roughly 300,000 kilometers per second. The furthest distance from which light could conceivably have reached us since the Big Bang is therefore, in a naive calculation, roughly 13.8 billion light years. Except that the universe has been expanding the whole time. The regions from which the light we are currently receiving was emitted long ago have, since emitting that light, been carried away from us by the expansion of space. A region that emitted light 13.8 billion years ago, light that is only just now arriving at our telescopes, is today not 13.8 billion light years away. It is roughly 46 billion light years away because the expansion of space has been carrying it further from us the entire time the light was traveling. The observable universe is therefore a sphere with a radius of roughly 46 billion light years. the distance to the furthest regions from which any information could have reached us. Its diameter is about 93 billion light-years. It contains, by best current estimates, something in the vicinity of 2 trillion galaxies. This is not a wall. It is not a boundary at which space ends or at which the universe stops. It is a boundary of information, a horizon beyond which no signal, traveling at the speed of light or slower, has had time to reach us. It is our horizon, specific to us, to our position in space and our moment in time. A civilization in a galaxy a billion light-years away would have its own horizon, overlapping with ours, but not identical. They could see regions we cannot see, and we could see regions they cannot. The horizon is not the edge of the universe, it is the edge of our universe, the edge of our view. And this distinction between the edge of what we can see and the edge of what exists is the central tension of this entire story. Because the two are almost certainly not the same, the universe almost certainly extends beyond our horizon. The questions are, how far? In what shape? With what properties? And does it have any edge at all? The geometry of space. To understand what lies beyond the observable universe, you first need to understand something that most people have never been asked to think about: the shape of space itself. Not the shape of the objects within space, not the shape of galaxies or the arrangement of clusters. The shape of the substrate, the three-dimensional volume in which everything exists. Space can, in principle, have different geometries, and those geometries have profound consequences for what lies beyond the horizon and whether the universe has any edge. The first possibility is that space is flat. Not flat in the two-dimensional sense, not like a sheet of paper, but flat in the sense that the rules of Euclidean geometry apply throughout. Parallel lines never meet. The angles of a triangle add up to exactly 180 degrees. The ratio of a circle's circumference to its diameter is exactly pi. Everything you learned in school geometry is exactly correct in every direction for all time. In a flat universe, space extends without limit. There is no center and no edge. Every point is as good as every other. The universe has no boundary, no wall, no far shore. It simply goes on. The second possibility is that space is positively curved. Curved like the surface of a sphere, but in 3 dimensions rather than 2. On the surface of a sphere, parallel lines eventually meet. Triangles have angles that add up to more than 180 degrees. If you travel far enough in any direction, you eventually return to your starting point. A positively curved universe is finite. It has a definite total volume, but it has no edge, no boundary, no wall. Just as the surface of a sphere has no edge despite being finite, a positively curved universe would be finite without having any boundary for you to run into. The third possibility is that space is negatively curved. Curved like the surface of a saddle, extended to 3 dimensions. In a negatively curved space, parallel lines diverge. Triangles have angles that add up to less than 180 degrees. A negatively curved universe is, like a flat one, infinite. It extends without limit in every direction. Cosmologists have been measuring the curvature of space for decades, using the cosmic microwave background radiation as their instrument. The microwave background is the afterglow of the Big Bang, the oldest light in the universe, released when the cosmos was about 380,000 years old. now stretched by the universe's expansion to microwave wavelengths. The tiny temperature fluctuations in the microwave background carry information about the geometry of the space they have passed through. The angular size of those fluctuations on the sky is exquisitely sensitive to the curvature of space. The answer, from missions including NASA's WMAP satellite and the European Space Agency's Planck satellite, is that space is flat, or at least flat to extraordinary precision. The measured curvature is consistent with zero, with an uncertainty of less than 1%. This means the universe is almost certainly infinite, or at least so large that the difference between infinite and very large is irrelevant for any purpose. And if the universe is infinite, then the question of what lies beyond the observable horizon has an answer that is both simple and almost impossible to truly absorb. More universe. The infinite beyond. An infinite flat universe is one of the most conceptually demanding ideas in all of physics, and it deserves more than a sentence. If the universe is genuinely infinite, then the space beyond our horizon contains more galaxies, more stars, more planets, more everything. An inexhaustible supply, extending without limit in every direction. Not just a lot more, infinitely more. More in the specific mathematical sense that the total number of galaxies in the universe is not a very large number, but a literally unlimited one. This leads immediately to a consequence that most people find deeply uncomfortable. In an infinite universe, with a finite number of possible configurations for the matter in any given region, because quantum mechanics limits the number of distinct states that matter in any finite volume can occupy, every possible arrangement of matter must occur somewhere. Not might occur, must. In fact, every arrangement must occur infinitely many times. This means that somewhere beyond our horizon, at an unimaginably vast but finite distance, there is a region of space statistically identical to our own observable universe, with the same galaxies, the same solar system, the same Earth, the same you. Reading this sentence with the same thoughts. And further beyond that, there is another, and another. An infinite number of copies, each separated from the next by a distance so large that the number of digits required to write it in meters would itself fill several observable universes. This is not science fiction. It is a straightforward mathematical consequence of an infinite universe combined with quantum statistical mechanics. The physicist Max Tegmark, who has done more than almost anyone to catalogue the implications of an infinite universe, calls these regions Level 1 parallel universes. They are not separate universes in the exotic sense. They are simply distant regions of the same infinite space, beyond our horizon, subject to the same laws of physics, but containing every possible variant on everything we know. The nearest identical copy of you in a typical infinite flat universe would be at a distance of roughly 10 to the power of 10 to the power of 28 meters. That number is so large that it cannot be usefully compared to anything. It is the distance at which the sheer combinatorial statistics of quantum states guarantee that your exact arrangement of particles must have appeared again. Whether this feels like a revelation or a reductio ad absurdum depends on your philosophical temperament. Either way, it is what an infinite flat universe implies. The finite without edge. But perhaps the universe is not quite flat. Perhaps it is so very nearly flat that our measurements cannot distinguish it from perfect flatness. but it is in fact ever so slightly positively curved. Like an unimaginably vast sphere, its curvature so gentle that no measurement confined to the observable region could detect it. In that case, the universe would be finite. It would have a definite total volume, but it would have no edge, no boundary, no wall to run into. Imagine again the surface of a sphere. But now imagine that you are an ant living on that sphere, and that the sphere is so enormous that you can only ever observe a tiny patch of its surface. From your perspective, the surface looks completely flat. You have no direct evidence of its curvature, and yet the sphere is finite. If you were to set off in any direction and walk long enough, you would eventually return to where you started. A finite, positively curved universe works in exactly the same way, extended to 3 dimensions. If you could travel fast enough and far enough in any direction, you would eventually return to your starting point. Not by reversing course, but by going straight ahead, around the universe. How large could such a universe be? The curvature measurements from the Planck satellite constrain it. The universe, if positively curved, must be curved so gently that its total circumference, the distance you would have to travel to make a complete loop, is at least several times larger than the observable universe. Probably much larger. Large enough that for all practical purposes, even in a finite universe, what lies beyond our horizon is an enormous additional expanse of space that we can never observe and that cannot, in any practical sense, communicate with us. There is another possibility in this category, one that is mathematically distinct from simple spherical geometry. The universe might have a non-trivial topology. Topology is the branch of mathematics concerned with properties of spaces that remain unchanged under continuous deformation, stretching, bending, twisting, but not tearing or gluing. The topology of a space is, in a sense, its connectivity. 2 spaces can have the same local geometry, both locally flat, for instance, but a completely different global topology. The simplest flat space is infinite and extends forever. But a flat space can also have the topology of a torus. Imagine taking a flat square of paper and rolling it into a cylinder, connecting the top and bottom edges. Then bend the cylinder around and connect its 2 circular ends. The result, in 3 dimensions, though it is difficult to visualize, is a torus. A torus is flat everywhere, just like infinite flat space. But it is finite, and it wraps around on itself. If you travel far enough in one direction, you return to where you started. A universe with toroidal topology would have a very specific observational signature. Distant galaxies in one direction would be the same as nearby galaxies in another. The universe's structure would repeat at regular intervals, like a wallpaper pattern extended to 3 dimensions. Searches for this kind of cosmic repeating pattern in the distribution of galaxies and in the microwave background have so far found no compelling evidence. But the absence of a detection merely constrains how large any such topological repeat distance must be. It would have to be larger than the observable universe. So we would not have seen the same galaxies twice. The shape of the universe beyond the observable boundary remains genuinely and deeply unknown. Inflation and the vast dark beyond. One of the most powerful constraints on what lies beyond our horizon comes not from geometry alone, but from the physics of the very early universe. Inflation, the period of exponential expansion that most cosmologists believe occurred in the universe's first tiny fraction of a second, has specific and dramatic implications for the size and nature of the universe beyond our observable patch. Before inflation, the region that would eventually become our entire observable universe was extraordinarily small, smaller than a proton. During inflation, it was stretched with almost incomprehensible rapidity to a size vastly larger than the observable universe. How much larger depends on how long inflation lasted and how energetically it proceeded, parameters that current theory constrains only loosely. The most conservative estimates suggest that the full post-inflationary universe is at least 10 to the power of 23 times larger than the observable region. Some models produce numbers far larger, 10 to the power of 1 trillion or more. Models that sit comfortably within the range of observational constraints can produce a universe so large that the observable part is, relative to the whole, even less significant than a single atom relative to the observable universe. Inflation also smooths out the universe. Whatever structure, whatever curvature, whatever irregularity existed before, inflation is stretched to invisibility. The post-inflationary universe is extraordinarily flat and smooth and uniform, which is why our measurements find it to be so. But this smoothness is a local property of our inflated patch. Beyond it, at the extreme edges of the inflationary expansion, at scales so large that even the post-inflationary universe is dwarfed, conditions may be very different. In the most widely studied inflationary models, inflation did not end everywhere at once. It ended in some regions, our region being one, but continued in others. New regions of inflating space were generated faster than inflation could end, in a self-perpetuating cascade. This is eternal inflation, the idea that the universe as a whole has been inflating without end since long before our local Big Bang, and continues to inflate today in regions so distant from us that they are permanently beyond any conceivable observation. In the framework of eternal inflation, what lies beyond our horizon is not simply more universe with the same properties as our own. It is a vast, churning sea of inflating space-time, a medium from which bubble universes are constantly nucleating and inflating into being, each one a self-contained region with its own post-inflationary physics, its own particles, its own forces, its own constants of nature. Our observable universe is one such bubble. It formed when the inflaton field, the quantum field driving the exponential expansion, decayed to a lower energy state in our local region, releasing its energy as the hot, dense plasma of the Big Bang. Other bubbles formed elsewhere at other times, through the same mechanism. Between the bubbles, the inflating sea, expanding so rapidly that the bubbles can never reach each other, can never communicate, can never be aware of each other's existence. What lies beyond our horizon in this picture is not more universe like ours. It is a multiverse, a collection of separate, self-contained bubble universes, embedded in an eternal inflating background, each one potentially governed by different physical laws, different particle masses, different force strengths, a different value of the cosmological constant. The bubble collision. There is one extraordinary possibility that deserves its own moment. Bubble universes nucleating in an eternally inflating space-time expand. They expand outward from their nucleation points, growing as their interiors continue to inflate. And so the eternally inflating space between them is also expanding so fast that bubbles which nucleate in the same general region will almost never reach each other. The geometry of eternal inflation does allow, in rare cases, for two bubbles to collide, not collide in the violent, catastrophic sense, not a crash that would destroy both, but a meeting, a grazing contact between the edges of two bubble universes, each one an entire cosmos in its own right, briefly touching in the inflating space between them. If such a collision occurred, if our bubble universe, early in its history, grazed the expanding edge of a neighboring bubble, the collision would leave a mark, a specific pattern imprinted on the cosmic microwave background, a circular disk of slightly different temperature, precisely round, with a specific profile of temperature variation from its center to its edge. Unlike any pattern produced by the ordinary physics of structure formation within a single universe. This is, remarkably, a testable prediction. Physicists including Matthew Johnson, Louis Lehner, and Hiranya Pires have worked out in detail what the signature of a bubble collision should look like in the microwave background, and have searched the data for it. So far, no confirmed signal has been found. The searchers have placed limits on the rate of bubble collisions our universe could have experienced without leaving a detectable mark. But the absence of a confirmed signal is not the same as a definitive absence. The collision, if it occurred, might have happened in a direction where our measurements are less sensitive. The signal might be too faint or too close to the edge of the observable region to be clearly distinguished from noise. The search continues. The idea that the first evidence for the existence of another universe might come from a faint circular smudge in the oldest light we can see is one of the most compelling and one of the most sobering possibilities in modern cosmology. If it were found, it would be the most important discovery in the history of science. The confirmation that we are not alone, that our universe is not everything, that beyond the horizon, in the inflating dark, other worlds exist. The many worlds next door. But the multiverse of eternal inflation is not the only kind of multiverse that physics contemplates, and the other kind is, in some ways, even stranger. Quantum mechanics, the theory of matter and energy at the smallest scales, is one of the most thoroughly tested frameworks in the history of science. Its predictions have been confirmed to extraordinary precision in thousands of experiments, and yet, as we have explored elsewhere, it contains a profound conceptual puzzle at its core, the measurement problem. When a quantum system is not being observed, the mathematics describes it as existing in a superposition of all possible states simultaneously. When a measurement is made, the system appears to jump, apparently randomly, apparently discontinuously, into a single definite state. The rest of the superposition seems to simply disappear. The many worlds interpretation of quantum mechanics, developed by Hugh Everett III in 1957, takes the bold position that nothing disappears. The superposition does not collapse. Every possible outcome of every quantum measurement is realized, not in one universe, but in a branching family of parallel universes, each one as real as the others, each containing an observer who sees a different definite outcome. In this picture, the universe branches continuously. Every quantum event, every radioactive decay, every photon absorption, every spin measurement splits the universe into copies, one for each possible outcome. The copies are identical up to the moment of the split and diverge afterward. This is not a picture of universes separated by vast distances, or by eternally inflating space, or by any kind of spatial barrier at all. The parallel universes of the many worlds interpretation coexist in the same space as our own, but in different branches of the wave function, different configurations of the quantum state of the universe, which do not interact with each other and cannot be detected by observers in any given branch. Whether this constitutes a form of beyond the edge depends on what you mean by edge. These parallel universes are not spatially distant. They are, in a mathematical sense, adjacent, neighboring branches of a universal wave function. But they are entirely inaccessible. No experiment can detect them. No signal can cross from one branch to another. They are, for all practical purposes of observation, as completely unreachable as a universe on the other side of an inflating sea. Many physicists find many worlds deeply unappealing, not because it is logically inconsistent, but because it is extravagant beyond any reasonable standard of theoretical economy. An infinite proliferation of parallel universes, constantly branching, none of them observable, all of them equally real. It is a steep price to pay for avoiding the measurement problem. Others find it the most natural and minimally assumptive interpretation of the mathematics. The wave function evolves according to the Schrödinger equation, and nothing else. No special collapse mechanism, no mysterious observer effect. Just the mathematics, all the way down, producing all outcomes simultaneously in a vast and branching quantum multiverse. The debate is genuine. The answer is not known. Other mathematical universes. There is one more category of beyond that must be mentioned. It is the most speculative, the most philosophically challenging, and the one that most directly confronts the question of what the word exists really means. The physicist and mathematician Max Tegmark has proposed what he calls the mathematical universe hypothesis. The idea that not only is our universe described by mathematics, but that every consistent mathematical structure exists as a physical reality. This is a radical extension of a position that many physicists already hold implicitly. We describe the universe with equations. Those equations work. They make accurate predictions. They capture the structure of reality with remarkable fidelity. It is tempting to conclude that the equations do not merely describe the universe, but in some sense are the universe, that mathematical structure and physical reality are the same thing. Tegmark's hypothesis takes this seriously and asks, if mathematical structure is physical reality, why should only a particular mathematical structure be real? Every consistent set of mathematical axioms describes a self-contained structure. The laws of physics as we know them are one such structure. The specific equations of the Standard Model and general relativity. But there are other consistent mathematical structures. Some would produce universes with different forces. Some would produce universes with different dimensions of space. Some would produce universes with no concept of space or time at all, only abstract mathematical relationships. If the mathematical universe hypothesis is correct, then all of these structures are equally real. Our universe is not special. It is one instance of a mathematical multiverse of unlimited scope and variety. Other universes are not elsewhere in space. They are not in different branches of the wave function. They exist in the same sense that the number 7 exists, not physically, not spatially, but mathematically, which is, on Tegmark's view, the only kind of existence there is. Beyond the edge of our universe, on this account, lies not space or inflating fields or quantum branches, but the full landscape of mathematical possibility. A collection of self-consistent abstract structures so vast and so varied that our universe, for all its 93 billion light-year diameter and 2 trillion galaxies and 100 trillion years of stellar evolution, is a single, specific, unremarkable instance. This is either the deepest idea in the philosophy of physics, or a category error of the most extravagant kind. The debate is genuine. The observable boundary as a physical thing. While all of this theory and speculation unfolds, it is worth pausing to examine the observable boundary itself more carefully, because it is not nothing. It is a real physical surface with real physical properties, and what it tells us is in some ways as remarkable as anything beyond it. The cosmic microwave background, the oldest light we can observe, released when the universe was 380,000 years old, comes to us from the edge of the observable universe. It is not simply a backdrop. It is a snapshot of the universe as it was at that specific moment, a photograph taken with photons that have been traveling for 13.8 billion years and have only just arrived. That snapshot shows us a universe that was, at 380,000 years old, extraordinarily smooth. The temperature variations across the entire sky are tiny, 1 part in 100,000. But those tiny variations are not random noise. They are the seeds of all the structure in the universe. The primordial fluctuations that, amplified by gravity over billions of years, grew into the filaments and clusters and voids of the cosmic web, into the galaxies we see today, into the solar system and the Earth and the conditions that made life possible. The pattern of those fluctuations carries information about the physics of the very early universe, about inflation, about the density of matter and energy, about the geometry of space. It has been analyzed with extraordinary care by cosmologists, and its implications extend not only inward, toward the physics that produced it, but outward, toward what the region beyond the horizon is likely to contain. If inflation occurred, and the evidence strongly suggests it did, then the physics that produced our observable universe was operating across a region vastly larger than what we can see. The same mechanism that generated the fluctuations in our observable patch was generating similar fluctuations in regions beyond our horizon. The same quantum processes, the same statistical properties. The universe beyond the horizon, in the inflationary picture, looks broadly like our own observable patch. Not identically, because quantum randomness ensures variation, but statistically, in terms of the distribution of structures and densities. This is the most direct evidence-based statement we can make about what lies beyond our horizon. Not the eternal inflating multiverse or the many worlds branching or the mathematical multiverse. Simply, more of the same. More universe, structured by the same physics, filled with more galaxies, evolving according to the same laws. The extraordinary is the ordinary, extended without limit. Why we cannot know. For all the richness of the theoretical landscape, there is a hard wall that deserves honest acknowledgement. The regions beyond our cosmic horizon are, in a very precise sense, inaccessible. Not inaccessible in the way that the other side of the planet is inaccessible. With difficulty, but in principle, reachable given enough time and technology. Inaccessible in the sense that no signal moving at or below the speed of light, originating in any region beyond our horizon, can ever reach us, and no signal we send can ever reach them. This is because the expansion of space carries those regions away from us faster than light can close the gap. The regions beyond our horizon are receding from us faster than the speed of light. Not because they are moving through space at superluminal speeds, which would violate relativity, but because the space between us is expanding, and the expansion of space is not subject to the light speed limit. The effect accumulates the further away a region is, the faster the expanding space between us carries it away. For regions beyond the horizon, the recession is so fast that no signal will ever bridge the gap. Not in one lifetime, not in the lifetime of stars, not in the lifetime of black holes, not ever. This means that the existence of what lies beyond, in any of the forms we have explored, can never be directly confirmed by any observation confined to our own cosmic bubble. The eternal inflation model, the many worlds interpretation, the mathematical multiverse. None of them produce signals that we can receive. They make predictions about our own observable universe as consequences of the physics that generated it, but they do not produce direct evidence of their own architecture. Some physicists find this disqualifying. If a theory makes no unique predictions distinguishable from simpler alternatives, if its key structures are in principle unobservable, then it sits outside the domain of science in the strict sense. The multiverse, in any of its forms, cannot be falsified in the way that general relativity can be falsified. It is not testable in the way that particle physics is testable. It is motivated by testable theories, but is not itself testable. Whether that makes it science or philosophy or something in between is a question on which reasonable people disagree. Others find this objection too narrow. Science has always dealt with unobservable entities. Electrons were predicted and accepted decades before their direct observation. Atoms were inferred from chemistry, long before any instrument could image them. The question on this view is not whether a theory's consequences are directly observable, but whether the theory is well motivated, internally consistent, and uniquely implied by frameworks that are themselves well tested. The multiverse is well motivated by inflation. The many worlds interpretation is well motivated by quantum mechanics. They may not be wrong just because they are, in their specifics, unobservable, but they may not be right either. What we do not know. The honest accounting is, as always, more nuanced than the headline. We do not know whether the universe is finite or infinite. The measurements constrain the curvature to be very close to zero, consistent with flatness, but they cannot rule out a very slight positive curvature that would make the universe finite. The difference between a perfectly flat, infinite universe and a very slightly curved, finite one that is 1 trillion times larger than the observable region is currently beyond our ability to measure. It may remain so permanently. We do not know the topology of space. A flat universe can be infinite, or it can have the topology of a torus or other compact space. wrapping around on itself at scales larger than our observable patch. Searches for the repeating patterns that such topology would produce have been inconclusive. The absence of a detection constrains the topology, but does not rule it out. We do not know whether eternal inflation occurred. Inflation itself is strongly supported by the observed properties of the microwave background. But whether it is eternal, whether it continues outside our bubble, generating more bubble universes, depends on the specific dynamics of the inflaton field, which are not directly observable. Eternal inflation is a natural consequence of many inflationary models, but not of all, and the distinction between models that produce eternal inflation and those that do not cannot currently be tested. We do not know whether the physical constants and laws of nature are the same in regions beyond our horizon. In the simplest models, they are. Inflation spreads the same physics uniformly across all post-inflationary space. In bubble nucleation models, they are not. Each bubble nucleates with a different set of constants determined by the state of the inflaton field at the moment of nucleation. Whether our constants are universal or parochial is currently unknowable. And we do not know, at the most fundamental level, whether the concept of beyond applies. If space is infinite, the question of what lies beyond has a straightforward answer: more space. If space is finite and closed, like the surface of a sphere, the question of what lies beyond the surface has no answer within the geometry of the space itself. There is no beyond. There is only the space, complete in itself, with no exterior for anything to lie in. The question, what lies beyond the edge of the universe, may be asking for an exterior that does not exist. Or the exterior may be everything. We do not know. The view from here. Look up the next time you find yourself outside on a clear night. Do it properly, not a glance between other things. Actually stop and tilt your head back and look at the sky. You might see a few thousand stars. On a very dark night, away from any artificial light, you might glimpse the Milky Way, the faint, diffuse band of our own galaxy's disk. So many stars packed so closely that they merge into a single glow. If you know where to look, you might find the Andromeda Galaxy, the most distant thing your naked eye can see, a faint smudge in the constellation it is named for, the light from it having left before modern humans existed. That is the observable universe from your eyes, the part available to you without instruments, without technology, without the extraordinary engineering of telescopes and satellites and signal processors that extends your reach to the horizon. And the horizon, the full observable universe containing 2 trillion galaxies and 10 to the power of 24 stars, is only the beginning. Beyond it lies more, far more. In the most conservative and well-supported understanding of cosmology, the universe extends far beyond what we can see, filled with more galaxies, more stars, more planets, more chemistry, more everything. That much is almost certain. How much more? By what factor the full universe exceeds the observable is unknown, but the factor is almost certainly enormous. Possibly infinite. And beyond that, in the frameworks that theoretical physics has been building for decades, motivated by the most successful theories ever developed, tested against the most precise cosmological measurements ever taken, there may be more still. Other bubble universes, each one a complete cosmos in its own right, forever separated from ours, by the inflating space between them. Other branches of a quantum wave function coexisting with ours in the same mathematical space, inaccessible to any measurement. Other mathematical structures, equally real if Tegmark is correct, equally rich, equally indifferent to the fact that we cannot see them. The edge of the observable universe is real. It sits at 46 billion light-years in every direction. We have mapped it with extraordinary care and measured its properties with extraordinary precision. We know with considerable confidence what the universe looked like at that distance and at the moment that distance was reached. But the edge of the observable universe is our horizon, not the universe's wall. Beyond the horizon, the universe continues. In what form, in what shape, for how long, with what laws, in how many versions? These questions have the most honest answer that any question can have. We do not know yet, but the fact that we have identified the questions, that we have built the mathematical tools to frame them precisely, the telescopes to constrain them observationally, the theoretical frameworks to generate competing answers and search for ways to choose between them, is not a small thing. The circle on the paper is not the paper. The dot inside the circle is looking outward, carefully, with everything it has. And the paper extends. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.